Hello, this is Dr. Moberly. We're going to look at the solution to a worksheet on a third order linear non-homogeneous ODE. Oh, I get the word ODE right there. It's ordinary differential equation. It's third order because third derivative is highest, therefore third order. The standard form P2y2 plus P1 of x, y plus P0 of x equals y equals r of x. Standard form, therefore linear. I guess it's actually maybe called the linear standard form. Another way to say it is no powers or exponentials involving the y terms. X terms can be anything, but not the y terms. And then, so that's why it's linear. And then it's non-homogeneous because r of x is not equal to 0 in standard form. Therefore, it's non-homogeneous. All right, write the characteristic equation and its roots. Obviously, we're talking about the homogeneous problem's characteristic equation. It is lambda cubed plus 3 lambda squared plus 4 lambda plus 2 equals 0. And need to consider positive negative factors of 2. Well, there aren't that many of them. Let's consider the plus 2, which would give us a lambda minus 2 factor, the plus 1, the minus 1, and the minus 2. Looks like probably 3 of those are going to turn out to be factors. Divide this into lambda cubed plus 3 lambda squared plus 4 lambda plus 2. We've got lambda squared. So I'm going to subtract lambda cubed minus 2 lambda squared. And this is going to be effectively 5 lambda squared addition problem there. Carry this down. 4 lambda, we try 5 lambda there. 5 lambda, lambda squared, minus 10 lambda. So this goes to 14 lambda plus 2. No, sorry, that is going to be 14 lambda minus 28. That is not equal to 0. That's going to be 30. Not equal to 0. That's the one that doesn't work. And let's try. So lambda minus 2 doesn't factor. Let's try another one before we run out of room. Let's try lambda minus 1 going into lambda cubed plus 3 lambda squared plus 4 lambda plus 2. That's lambda squared, lambda cubed minus lambda squared. Again, we're subtracting the whole thing, so that's going to become 4 lambda squared plus 4 lambda. That's going to become 4 lambda squared minus 4 lambda. So this becomes 8 lambda plus 2. Actually, that doesn't work. Let's try another one. Lambda plus 1. So this is the lambda equal to -1 choice here. Hopefully that one's good. Lambda cubed plus 3 lambda squared plus 4 lambda plus 2. This is going to be a lambda squared, lambda cubed plus lambda squared, which we're subtracting. We get 2 lambda squared plus 4 lambda. So that's going to be 2 lambda squared plus 2 lambda. And that's going to give us 2 lambda plus 2, which looks like a 2. All right, that one works. Let's go ahead and take this, put it into the quadratic formula, hopefully find those other two roots. It's going to be a minus 2 plus or minus square root of 2 squared minus 4 times 1 times 2, all over 2 times 1. So you go minus 2 plus or minus 4. Oh, that's why. Haha, the other roots are going to be complex. So that looks like 4 minus 8 goes with minus 4 all over 2, which is equal to minus 2 plus or minus 2i over 2, which is minus 1 plus or minus I. All right, so we would have exhaustively had to go through all four possibilities to find the one real root. I got one real root and two complex conjugate roots. They're complex conjugate pair, I guess is the right way to put it. And now it's time to write the homogeneous basis. This is one of the ones that worked, so that's going to become e to the minus 1x. Go ahead and put a comma there. This one's going to become e to the minus 1x cosine 1x. And it's also going to give us e to the minus 1x sine 1x. Now these are the real solution functions, not the exponential e to the minus 1i x, not the complex. Perfectly okay to write a basis with the complex exponentials, but it's just not, it's not going to be a habit that you're going to want to use, because I'm not asking you to prove Euler, I'm just asking you to use it. So what's the solution to the homogeneous problem? Well, it's going to be a linear combination of these. C1 e to the minus 1x plus e to the minus 1x a cosine 1x plus b sine 1x. So there's a purely real solution. And we could shorten it up a bit. What applies, what doesn't apply? Notice we've got an e to the minus 1x. E to the minus 1x is in the homogeneous basis. Now there is this other factor, e to the minus 1x, but this is not requiring modification of the e to the minus 1x in R of x. Only if there was an e to the minus 1x times sine or cosine in this original R of x would we have considered that. So the original R of x just includes a real exponential. So basic would give us y of p equal to some k e to the minus 1x. However, this is in homogeneous basis, so modify to give yp equal to kx e to the minus 1x. And no sum since only one term in R of x. Of course, the sum rule might not apply even if there were multiple terms. Just so you know, there's 3 rules. And they need to be mentioned by name even if they are not applied. So there would be certain combinations of terms on the right-hand side with R of x that would require the sum rule. Using the method of undetermined coefficients. All right, we're ready for the use of the product rule. Y tick p is going to be equal to kx to the 1. I'm sorry. Going to be equal to k times e to the minus 1x plus k times x times minus 1 times e to the minus 1x. This is product rule. And unfortunately, we're going to have to do it several times. So we got the product rule going on there. Y double prime p. Well, this is just going to be minus 1 k e to the minus 1x. This is going to be product rule again, 2 terms. And this is going to be k times minus 1 e to the minus 1x plus k x minus 1 squared e to the minus 1x. And y triple prime p, this is going to be minus 1 squared k e to the minus 1x plus k minus 1 squared e to the minus 1x plus, now we've got the product rule again, k minus 1 squared e to the minus 1x plus k times x times minus 1 cubed e to the minus 1x. Wow, all right, we're just barely going on how to apply the product rule. I'm sorry, how to apply the method of undetermined coefficients. Okay, looking back at the differential equation, the ODE here, we're going to apply that down here. And note that the only terms we really need are the terms that involve e to the minus 1x. So, oops. Let's make this an e to the minus 1x that factors everything out. And let's look at the third derivative. We don't want any of the x e to the minus 1x terms. Forget these. Because we really only need one equation to solve for the one unknown, which is the coefficient k. So looking at this, we've got from the yp term, yp triple prime term, we've got 1, 2, 3k. From the 3yp double prime term, we've got 3 times, and this is this and this multiplying by k, so we get a minus 2k. And from this part, I've got 4 times k, and then the 2 times the original thing, that's actually going to be nothing. There is no just e to the minus 1x term there. And then the right-hand side is going to be the 2. I have one equation for k. It looks like 3 minus 6 plus 4. 3 and 4. So k is equal to 2. I think we're done. Oh, okay. Now let's write the general solution out. Y equals YH plus YP, which is equal to, scrolling back up for just a second, that's right, 1 and I, C1 e to the minus 1x plus e to the minus 1x a cosine 1x plus b sine 1x plus 2 e to the minus 1x x, the modification. And we want to take the derivatives. So let's go ahead and do that. Minus 1c minus 1x. Oh boy, product rule. Here we've got minus 1 e to the minus 1x times a cosine 1x plus b sine 1x plus e to the minus 1x times, well, just a 1 is going to pop out, and actually it's going to be a negative sine 1x times a. Sorry, I have to squeeze that out of there. A times that plus b times 1 times cosine 1x. And then plus minus 1. Oh, this product rule here. I think we've done this product rule before, but it's going to be a 2e to the minus 1x plus minus 1 minus 1 times 2 times e to the minus 1x times x. So that's our first derivative. And our second derivative, a little bit more work, is going to be minus 1 squared c1 e to the minus 1x. I've got a product rule applying here. So that's going to be minus 1 squared e to the minus 1x a cosine 1x plus b sine 1x. The second term is going to be minus 1 e to the minus 1x times a negative sine 1x plus b cosine 1x. And there's going to be a second one of those from here. That's going to be another minus 1 times e to the minus 1 a negative sine 1x plus b cosine 1x. And then there's going to be the second term from this product rule, which is going to be plus minus 1 squared. No, not minus 1 squared. sorry, that's going to be the original e to the minus 1x times minus a cosine 1x minus b sine 1x plus two more terms, scrolling down just a little bit, actually three more terms, plus 2 times minus 1 e to the minus 1x plus another one of those, 2 times minus 1 e to the minus 1x plus a negative 1 squared to e to the minus 1x times x. So I've applied the product rule. This I took the derivative of, and this split into two pieces by the product rule. And it asks us to go ahead and plug some things in with the zeros. So, plug in zeros into the y equation. Let's go with y of 0. Well, that's going to be equal to c1 plus a, and that's it. This doesn't contribute anything. The sign doesn't contribute anything. The second equation of interest, the y prime of 0. Oh, by the way, that's given to be 1. The second equation is going to be minus 1c1 minus 1 times a, coming from here, and then we're going to get this, which is going to be plus b, and then plus 2, and then this doesn't contribute anything because when the x is multiplying out of 0, you're going to get 0. The third equation, and let's do this one in light blue I've already used. Do this one in pink again. Now y double prime 0. I forgot to mention that this is equal to 2 as given. So y double prime 0, we're going to take this term, which is going to be c1. We're going to take this term, which is going to be actually plus a. We're going to take this term, which is going to be minus b. We're going to take this term, which is going to be minus b. We're going to take this term, which is going to be minus a. And then this term, which is going to be, minus 2. This term, which is another minus 2. And then this doesn't contribute anything because of the 0. And that total is equal to 3. Now, admittedly, we've got 3 equations, 3 unknowns. We'll be able to solve for a, b, and c1 in just a moment's time. Okay, I think I had to start this to build up the confidence to do it, but the first equation gives us a substitution so that c1 will be equal to 1 minus a in the next equation. So then we're going to substitute the c1 to get this. This becomes an equation. Interestingly enough, this a cancels out here. The minus 1 doesn't. We get a minus 1 plus the b plus 2 equals 2. Subtract the 2 from both sides, and we've got a 0. So b is equal to 1. Now we're going to use the third equation, because that doesn't help us go back to the first equation just yet. And we've got a 1 minus a plus a minus 1 minus 1 minus a minus 2 is equal to 3. I think we can solve this for a. We've got minus a, and then we've got minus 1. We've got a 1 minus 1 minus 1, minus 2, minus 2. So we've got a minus 5 minus a is equal to 3. Minus a is equal to 8. A is equal to minus 8. I think we have a particular solution to go with our initial conditions. And just recalling what the solution function looks like. That's right. Okay, so we've got our y is equal to C1 is going to get figured in. Oh, so therefore C1 is equal to 9. So we got a 9 e to the minus 1x plus e to the minus 1x times negative 8 cosine 1x plus 1 sine 1x plus 2 e to the minus 1x x. Alright, there's our particular solution and our homogeneous solution with the coefficients all solved. And we're done.